All right, good morning. Okay, we started talking about probability on Monday, and so today we're expanding on that a little bit. Just as a reminder, probability of some event happening is really the number of winners, the number of things that we want, the number of favorable outcomes over the total possibilities. So it's what we want over the total possibilities. How many winners do we get over the total possibilities? It's a really easy thing to figure out usually. So that is theoretical probability, okay? And theoretical is how it should happen in a perfect world. If we could do it 1 billion times, then this is what it would end up being. So today we're talking about experimental probability and seeing how they're a little bit different. So theoretical probability is what should happen. It's what should happen in an experiment. It's what should happen, not necessarily what actually happens. So, for example, if you toss a coin 100 times, if you toss a coin 100 times, how many heads would you expect to have? 50. You'd expect to have 50 heads. That's exactly right. And so, anybody else need notes back it? All right. So we would expect to have 50 heads. You expect 50 heads and 50 tails. That's what you would expect. Unfortunately, that's just really not how probability works. 100 is not many times. Seems like a lot, but theoretical probability is if we did it an infinite number of times. So if we sat here forever and flipped a coin, okay, if we did it forever, then yes, we would get half heads and half tails. That's hard to do it forever, isn't it? It would take a really long time. Okay, all right. So experimental probability is what actually happens. What actually happens after an experiment of many trials. Now, we can do a lot of trials. We can do 10, 20, 30, 40, 50 trials. That's not too hard. But it's hard to do an infinite number of trials, and that's theoretical probability, if we could do it forever. All right, so we're going to do a little bit of an experiment here. We're going to use the game rock, paper, scissors as an example to compare the theoretical and experimental probabilities. So does anyone not know how to play rock, paper, scissors? Okay, we're just checking. Okay. So first we're going to fill out this theoretical probability here. We want to complete the table below showing who would win in the game under the different combinations. And so we've got player A and we've got player B. And if they both rocked out, what's that? Tie, so no winner there. Okay, nobody wins there. If player B had paper and player A had rock, who wins? Paper wins, right? So player B is the winner. If player B has scissors and player A has rock, who wins? Player A is going to be the winner there with the rock. The rock is going to win. The rock. All right, rock and paper, who wins? Player A wins there. Let's see. Oh, paper and paper? Tie. Nobody wins. Okay. And then paper and scissors. Player B is going to win. And then last we got scissors and rock. Who's going to win? Rock is going to win. That's player B. We've got paper and we've got scissors. Which player wins? A is going to win. That's the scissors. And scissors and scissors is a tie. Okay. So what is the probability of player A winning? We have 1, 2, 3 wins. So 3 wins out of 9 possibilities there. And 3 out of 9 reduces to 1/3. Yes, if we were to divide by 3, top and bottom, we would get 1/3. Okay. What's the probability of player B winning? Yeah, again, we've got 3 wins out of 9 possibilities there, which again is 1/3. And what's the probability of a tie? 1/3 again. Again, we've got a tie 3 times out of 9, which reduces to 1/3. So those are the theoretical probabilities. So what I want you guys to do is you're going to play with your partner here, the person sitting next to you. And Stevie, do you want to come over here so you can play over here? That'll be fine. Rock, paper, scissors with your partner. Tally how many times partner A wins and how many times partner B wins, and the number of ties. So you're just going to do the whole, like, 1, 2, 3, 4 cross, tallies, okay? So I'm going to give you guys about 5 minutes to play with your partner, figuring out who's going to win in rock, paper, scissors, okay? Stevie, will you come over here? All right, go. Okay, so you guys all have, all have different trials. But that was kind of fun watching you guys play. So you all have different outcomes here. And so did anyone get that partner A won 1/3 of the time, 33%? Anybody get that? No? How many times did partner A win? 28? 41? 20? Yeah, it was all different. 44, is that what you said? 45%? All right. So they were very, very different. And so I'm just going to pick, because that's an interesting one there. Nam and Jace, what were your numbers here? How many times did partner A win? Yeah. 19, because that's really interesting. So, and partner B won how many times? 9. And how many ties did you have? 13 ties. Holy moly. So this is over your 25 trials. How many total trials did you do here? Oh, 14 ties? Okay. Wow, it was 42? Okay, so 19 plus 9 plus 14 was 42. Okay. So they did 42 rock, paper, scissors sessions, and so that's kind of interesting. So partner A won 19 out of 42 times. Ooh, baby. 19 out of 42. Ooh, that is 45.2% of the time. Wow, that's a lot different than that. That's pretty interesting. Partner B would have won 9 out of 42 tries. 9 out of 42. That's 21.4% of the time. And then a tie would have been 14 out of 42. 14 out of 42 was, hey, that one was 33.3%. That's kind of interesting. That is 1/3. Math frac. Look at that. That is 1/3. Hey, that was one thing that actually did work out theoretically as predicted. That's kind of interesting. So this is the difference between theoretical probability and experimental. It's going to vary a lot because doing 42 trials is still not nearly enough to be an infinite number of trials. But kind of interesting. So do the theoretical results match the experimental results? No. All right, and then how could the experimental results get closer to the theoretical results? What's going to make our experimental results approach if we do it what? On purpose? So cheat, you mean? Yeah, maybe. But how do we get these experimental results to get closer to the theoretical ones? Do it forever, yeah. If we do more trials. So if we were to take all of our trials and add them up, then we will get closer to the theoretical results. So maybe we would do that another time. Let's turn the page. Number 9. The table shows the results of rolling a standard die 50 times. What does this table mean? Like, what does this 5 mean? The 5 on the dice, so the 5 side, and what does the 12 mean? Yeah, how many times we rolled a 5? So we rolled the 5 12 times, okay? We rolled a 3 9 times. So frequency is how many times it happened. What is the theoretical probability of rolling a 4 on a standard die? How many options are there when you roll a die? 6. It's 6 sides. And how many winners are we looking for? 1 winner. So the theoretical probability would be 1 out of 6. There's 1 winner. That 4 is the only winner. And there's 6 outcomes that would possibilities. What is the experimental probability of rolling a 4? 5. There were 5 right here, but 5 out of how many? Yeah, all of these added together. We got to know how many trials we did here. So we're going to total this up, add these things together. 4 plus 10. Oh, look at that. They told us they rolled 50 times. Let's just make sure. 9 plus 5 plus 12 plus 10. 50! Look at that. They told us they rolled the die 50 times, but if they didn't, we could just add all our trials up. So this is 5 out of 50, and what does that reduce to? 1 over 10, 1/10. What's bigger, 1/6 or 1/10? 1/6 is bigger. Yeah, this is lower. Compare this to the theoretical probability. Lower than expected. All right, it is lower than the 1/6. And of course, if you didn't know that, 1/6 is 16.6%, and 1/10 is 10%. All right. So you could put it in the calculators. All right, let's look at number 10. The results of spinning the spinner on the left 75 times are shown below. So again, this is like they spun a C 10 times. What's the theoretical probability of spinning a shaded letter? 6 out of 8. 6 out of 8, which reduces to 3/4. All right. What is 3/4? 75%. 0.75, which is 75%. Okay. All right. So there are 6 shaded out of 8 possibilities there. What's the experimental probability of spinning a shaded letter? Let's see. What are the shaded letters? A, B, C, and E, F, G. So there's our shaded letters. How do we figure out how many times we landed on a shaded one? Add them together. Very good. 5 plus 12 plus 10 plus 11 plus 13 plus 9. So if I add all these up, that gives me 60 shaded winners out of 75. Where'd the 75 come from? Adding them all up, or right here it told us that we did it 75 trials there. Let's see, what is 60 out of 75? Let's see, 60 out of 75 is 0.8, which is 80%. So compare the theoretical probability and the experimental. Was it what we expected? How does this experimental compare? It's higher. Higher than expected. It's pretty close, though. 80 is pretty close to the 75%, so a little higher than expected. Interesting. Okay. So we can also use this information to predict how many things we're going to get, what we would expect to happen. This is called expected value. So let's see, here on number 11, we are tossing a coin 100 times. So this is the experimental data that we toss the coin 100 times. But theoretically, how many heads would we expect to occur in 300 tosses? Yeah, so if we know that theoretically the probability of getting a head, the probability of getting a head would be 1 out of 2. And if I toss 300 tosses, then I would expect us that we would get half of 300. I would expect that we'd get 150 heads if we were to use the theoretical probability. But let's look at our experiment. So let's use our data. What was the probability of getting a head based on our data here? How many heads did we get using the data? 58 out of 100, okay. And 58 out of 100, if I want to figure out how many heads we would expect in 300 tosses, what do I need to do? Yeah, multiply it by 300. So 58 out of 100 times that 300 would give us what we need there. So let's see. Yeah, I'm going to type that in. So 58 out of 100 times the 300, and we get 174 heads. Okay? So you can take your probability and just multiply it times the number of trials. Sign up, please. All right. I don't like number 12. Do you guys have any questions for me? All right. You guys have adults in math.